Today we will continue to solve some example to analyze the first order circuit in the case of the constant input. Um, Before to solve example, I will give you the brief review about how to solve the first order circuit. And it's very simple. For example, we have the general form of a circuit like dt d xt plus a xt equal fx. F is not unknown, but it kind of a function of x. Then the solution of xt will be sum of xnt plus xft. xnt is natural response, and fx is forced response. In the case of the four-star circuit, the system equation can be written in this way here. It's a first order derivative and the zero order the derivative terms, and this is the first input. Then in the case of this equation, x and t can be written in general form. It will be k exponential minus 1 over tau t minus t0. Here t0 is a time instant to be applied the variation. For example, switch is turned on. Example, switch is closed or open, and so on. Then this is the step to solve this equation here, and this is natural response to form, and xft is the forced response. The forced response depends on first input fx. If fx is constant, then xft is constant. And fx is a sinusoidal, then fxt also sinusoidal. fx is exponential, then fx also exponential. Then we are ready to solve the first circuit in here. What is the first step one? Step one is to find steady state before disturbance. That means the switch is before switching is turn on, turn off, or to close. Why we should do that? Because we need what the initial condition. It could be current inductor or current of inductor or the voltage of the capacitor. It could be required. And step 2 is we need to find out the steady state find steady state after disturbance. Why? We need the first response. Then step 3 is to find complete solution. Where's that? xt is xnt plus xft. Based on step 2, we get the f xft. So xt will be general form over here, k exponential minus 1 over tau t minus t0 plus xft here. And based on this second, we can gather the example of dt dxt plus a xt go ft. Here a is same as 1 of tau, so we have it here. So we have one more unknown variable, that will be k. So how to solve here is x t0 is the initial condition. Is you can say here t0, then there's 0, so k plus xf t0 here. Based on here, we can calculate k. Then final solution is k exponential 1 over tau t minus t0 plus xf t. In this time, we know all variables. We know k, and we know 1 over tau, and we know fxt. That's the final complete solution of first order second. We will use this step to solve the first or second. Okay. There will be an example, the find capacitor voltage in the circuit here. So we'll use the example here. Okay. We'll copy here and we'll use it. Example 3.3. Find capacitor voltage. Yep. Okay, then what should we do first? It's very simple. We need to figure out the circuit. I mean, this circuit change based on the switches. So before switches t equals 0, the switch is open. So the first circuit looks like here. It looks like here. What it says. Okay, I will use another color here. 12, because this is not closed. This is open, so this is 10 kilo ohm is a reasonable value, and 330 kilo ohm and 60 kilo ohm and capacitor here. 2 microfarad. This is a VT. Based on here, d circuit is smaller than 0. Then because this is the steady state, so capacitor is open, so VT will be 10 plus 30 plus 60 and 60, 12. So this is quite simple. This is 6, 10, 12. There be 7.2 volts. So we know that VT minus, 0 minus is the initial condition here, 7.2. There will be initial condition. Next, we will solve this circuit in the time is less than 0. So T and here, then we can draw. That is because this is closed, so this is ignored. So our circuit is simple, more simple. 12, 30 kilo, 60 kilo, and capacitor here. 2 microfarad. This is a VT here. So in problem, they require to use Thevenin the equivalent circuit here. So we can do that here. So I will divide this and I will see this side of a view here. Then this circuit looks like here, 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 and 60 kilo, 1 kilo, and 12 volts. Referring to here, VOC will be 30, 60, 60, and 12. So how much is it? 8. So VOC is 8 volt. Then voltage is LT is 30 kilo and 60 kilo is parallel connected here. So there is 1/30, 1/60, and 60. 3 here is 20 kilo ohm. So this circuit rewritten here, redraw here, is 8 volt. This is 20 kilo ohm and capacitor 2 microfarad and VT. It looks more simple where T is larger than 0. So it's quite simple. Based on this equation, this circuit, we can derive the VT. What is a VT? VT is a division over here. So we define this current over here, IT. Therefore, 8 volts, the same with 20 kilo ohm multiplied by IT plus this voltage is VT. But IT is going through this capacitor. So we know that IT is the same as C dVT because this current flowing through this capacitor. So there will be 2 microfarads, 2 multiplied 10, 6 dt dV. So we insert this current to here. So our equation can be written again. A is 2, 3, and 2, 6 dt dv plus v, 3, 4. So that will be written here. Actually, if you use that number but the symbol here, actually that was, we can define R and C, there will be R, and that value was C. So actually, and this is a V in. So we written here V in is RC dt dv plus vt. So based on here, we can read it in the equation. dt vt plus 1 over RC vt is equal 1 over RC v in. So we got it. You got it. That is problem. What is RC? Okay. Oh, we need more space. What is RC? R is 20 and kilo ohms. C is 2 micro. So RC is 40 10 minus 3. So that will be 0.04. So there will be dt dvt plus 25 vt equal 25, and v in is 8. So there will be 200. Am I right? So okay, we'll use coffee here. We will solve this equation here. So what is the Vt? The Vt is a Vnt plus Vft. So what is a Vft? We have to solve the Vft. Vft is a steady state response of the final second. That will be here. So because 8 volts, the capacitor, so in the steady state, the capacitor is open circuit, so no current here, so Vt is 8. So we know that the Vf infinity is 8. So Vt will be k exponential minus 1 over tau t minus t0 plus 8. And here, what is the tau? 1 over tau is 25. So k minus 25 t minus t0 plus 8. This is time we describe the k. We have to use the initial condition. When t is 0, that value is 7.2. So V0 minus is 7.2. So in here, V0 minus is equal to 0 plus, there will be 7.2 because t is 0. So k plus 8. Therefore, k is minus 0.8. So we can read it here. The Vt will be insert here. Minus 0.8 exponential minus 25 t, because t0 is 0. because the switch is open at the t equal to t0 is 0 and plus 8. So there'll be solution of the voltage of capacitor. This is the way how to solve the problems here. We have another example over here. Define capacitor voltage after switch is open. You know, this is the same circuit, 8 volt. Okay, you can use it. You can use it. Compare here. So, that is the same circuit. This is 8 volt. This is 8 volt and 10 kilo ohm and 2 microfarad and 2 volt here. But the important thing is, in the example, previous example, when time is 0, switch is open. But in this case, time is and switch is open when time is 50 milliseconds. There's only different things, 2 examples. When we need to know the solution over here, we already got that solution was that values. That was the solution over here. That was it. You compare over here. Only different thing is that values than here. So we will compare 2 solution. That is the solution here. Okay. This example A, 3, and 6. Okay. Plus minus 8 volt, 10 kilo ohm. This is capacitor and 2 microfarad. There is no voltage here. We want to know here. Open T is 50 milliseconds, and there are 2 volts are the voltage source here. Looks like that. So, okay, I will solve this example as this is the first time to solve here. Okay, the first, what should we do? The first, we need to find the initial condition. So second, in the case before t is equal to 50 milliseconds, the circuit looks like here. 8 volt. Looks like here. 2 volt. This is a VT. This is 10 kilo ohm. This is 2 microfarad. So VT, when t is 50, actually we'll use the second unit, 0.05 minus the same meter 2. Why? In the steady state conditions, capacitor is a kind of open circuit. So this is nothing here, no current here. Therefore, Vt is same with the 2 volts. And that will be initial condition. Then what should we do next? We redraw the circuit in our constant time here. Then because circuit is open, so circuit is a little bit different. 8 volts, 10 kilo ohm, and then on the capacitor here, 2 microfarad, and this is a Vt here. So what should we do? We need to make equation based on here. So we define this current is It. So the solution is 8 volt is same with 10 kilo ohm and It plus Vt. We define this is R. So A is actually, we use a symbol, not the values. This is R, this is a V in. So V in is R, It plus and Vt. Because It going is It flow through the capacitor. So we got the information is Vt, no Vt, It is C dt dV here. So C is 0, C is 2 and this farad because it's a microfarad here. So we insert current here. So V in is RC dTd Vt plus Vt. Therefore dTd Vt 1 over RC Vt is equal to 1 over RC V in. This is a, we repeat this equation. This is a general form of the capacitor inductor, resistor capacitor, the simple, the first circuit. So we know that 1 over RC will be R is 10, 4, C is 2 minus 6. So over 2, 50. So from this equation, what you can get in? We got our Vt is K exponential minus 1 over tau. 1 over tau is the same with 1 over RC. So there will be 50. 50 T minus. So the important thing is what happens this second when it happens. 50. So 0.05 multiply VFT. What is the value of VFT? Because this is the state in the case of this station. So this is capacitor, so this is open circuit. So Vt is 8. So we can written K exponential minus 50 T minus 0.05 plus 8. Then we need to know the K. How to use it? How can solve it? We use initial condition of here when at the time V is 0. So T insert 0.05, 0, so 1, so K plus A was 2. Therefore, K is minus 6. So complete solution of Vt is minus 6 exponential 25 minus 25, okay, minus 25 T minus 0.05 plus 8 volts. That is solution over here. So that is a final solution of this example here, and we compare that is here. Oh, we have some mistake because this is 50, so this is why this is 25. I'm sorry, this is a minus 50. I'm wrong. It's my mistake because we used 50, so there will be minus 50. So there will be not 25, there will be 50. So minus 50. So you can compare two equations here. So in the case of the first example, what's the difference thing? The new thing is this part. The example, the change happened at t is 0. So when t is 0 here, but in the example, now the time is happening and is 0.05 because this is not 0.05. So actually, the complete, the more exact solution of this equation, this circuit is looked like here. In the case of here, Vt is 2 volt when t is smaller than 0 second, and minus 6 exponential minus 50 t plus 8 volt when t is larger than 0. So in the case of Vt, the more exact solution is 2 when 2 volt when t is 0.05 second, and minus 6 exponential minus 50t minus 0.05 plus 8 volt when t is 0.05. Actually, this is a more exact expression to describe the Vt here, because this solution is satisfied when t is larger than 0.05. Okay, next we will discuss about the sequential switchings. It's not difficult. It's simple. But it looks like more complicated because when one circuit contains not only one but also two or more switches that change state at different instant, that is called the sequential switching. How to solve this problem? It's very simple. It's the same way. You can use the same method based on the fact that inductor current and capacitor voltage do not change instantaneously. That is the basic assumption to solve the first order circuit. You can use the first order differential equation and use the general form of that. That's it. But the change happens when second time when the switch is 2. And then we need to divide the time slot based on the time instant the switch is turned on, turned off. Then we solve the different equations in every instant. We'll give you some example here. This is the example. We have to solve the problem here. Okay. It's quite complicated. We will do this step by step. This is an example. We'll use this again. Okay, let's see. There are two switches the here and here, and this switch open, or actually when time is 0, this switch is moved from here to there. Then at time t is 0.001, 1 millisecond, the switch is closed here. So we need to check the circuit in the point of the time. This is time t, and this is 0, and this is 1 millisecond. That means here we have circuit 1, there are circuit 1, and here circuit 2, and here circuit 3. And at every instance, in here, they are transient, and also they are transient. So we need to solve the first circuit at this moment here, and we need to solve again the first circuit at this moment. That's only different thing. Everything is the same. So we need to start at this point here. So when t is 0, small 0, then this circuit looks like here. Is a current source, so 10 ampere, and because this at before t is 0, so switch is connected here, so there will be inductor here, and there are 2 ohm resistor. There's a 2 millihenry and 2 ohm here, and you define this current is IT. So why we need to this circuit? Because we need to what we need here? Because we need to initial condition of this state. So why is the IT 0? IT equals 0 minus, because when the steady state, capacitor is open. In other words, inductor is a short current. So all current going through these 2 millihenries. So there will be 10 when t is here. So that will be initial condition. Then we need to do this for when in this instant. Here we need to figure out the circuit. Here, during that, switch is moving here. So there are open circuits. So no current going through here. This is current rotating here. It's not going to the dialysis. And this circuit is not closed yet because this is 1 millisecond. So only remaining circuit is connected here. So for this time, they will need inductor and resistor here. So this is L and this is R. L is 2 millihenry, R is 2 ohm. So there is a VT, this is IT. The based on here, we define that this current is IR. So based on this node, we make a KCL. What's KCL? This current is out of the node minus IT minus ILT is 0. It's very simple. Then what is IL? ILT is R. Is it because so this will be the same with that here. So VT divided by R. And what is a VT? VT is defined L dTd IT here. So we will use this circuit. VT is insert, excuse me, VT is insert here, right? VT is insert here, and IL is going to there. So minus IT minus IR will be 1 over R, VT is 0, and VT here. So minus IT minus 1 over R, L dTd IT is 0. Based on here, we can rewrite the equation dt it plus L R over L, R over L. Actually, we can read it here. This is 1 of here. In this way, you can read it in here. IT will be 0. So it's quite simple, because IT is INT plus IFT. So we just in this point, we just will be check out only this circuit. So to get the IFT here, we consume that even though the time, if this circuit is defined from the 0 to 1 millisecond, to get the IFT, we use infinite time. So there are no full source here, so that will be 0. So this is a 0. Why? Because I infinity will be 0. So that will be k exponential, that is a 1 over tau minus 1 L divided by R is T. That's it. Then what's the derivative over here? L is 2 millisecond and 2 millihenry. R is 2 ohm. So LR is 0.002 divided by 2. So there will be 0.001. So there will be K exponential, because of here, minus 10 T. So we took, to get a K, we can use the initial condition over here. What is the initial condition here? 10 volt. So we insert 10 is 0 minus, is a K will be 10. Therefore, IT will be 10 exponential minus 1000 T. So that is a reasonable when time is, when this is reasonable. This is 0 to 0.001 second. Then we need to do this one more time. When t is larger than 1 millisecond, we need to solve the second differential equation here, the second one here. So in the point of what is the initial conditions? Initial condition is t is 0. This is, I'm sorry. Sorry. Let me see. We do this here. Oh, excuse me. We do this here. This is again. We do this here, and this is again. Based on here, we got the current value over here. Next thing is we need to know about that. The point of the circuit 3, we need to know the initial conditions. So we will discuss about the circuit 0.001. Things large here. Then what is the initial condition? That will be 1 millisecond is the initial condition. So, what is a circuit? In here, circuit looks like, before t is 0.001 minus, then circuit is this is circuit L R. Okay, we will use small L R. So that will be IT. This can be derived right here. So there will be 10 exponential minus 1000 t ampere for t is larger than 0. So I 0.001, that will be 10 exponential minus 1000 0.001. There will be 10 over E. So that value is 3.68. So that is the initial condition. That is initial condition. Over here. So based on that, we can redraw the circuit again. We know when switch is turned on, then there are one more 2 ohm resistor is connected in the parallel here. Then circuit is a little bit different. Twinly is L, and this is a resistor, which is R. That is not 2. There is a 2 parallel 2 is 1. So circuit is a little different. So based on here, we have to derive the electric circuit equation. Define this is the VT, then you define the same way IR, then IL is VT divided by R, and we define this is IT, and IT will be IR. Then VT is L dTdIT. So you add in here. So we'll use blue pens. Here, IT equal IR. IR is 1 of R VT. VT is that values L dTd IT. So we written here dTd IT minus actually this is not, actually no, this is minus, so we need it, okay, plus 1 over and divided by R, IT will be 0. So we know this is a simple equations. So IT will be INT plus IFT. Here, because this is no source, so when time is infinity, so there will be short circuit, so no source, so there will be 0. So IT is simply K exponential minus 1 over tau T minus T0 here. Here, 1 over tau is 1 over L divided by R. Here, 1 is L is 2 milli, 0.002 divided by R is 1. No, actually, not 1, so there will be 1 over 0.002, that will be 500. So it will be K exponential minus 500 T minus, when is T0? T0 is 0.001. So there will be 0.001. So what should we do? We should get the K. How to get here? Initial condition. We use initial condition over here. I 0.001 is K will be 3.268. So IT will be 3.68 exponential minus 500 T minus 0.001. That's a solution. So we can summarize IT. IT is, first there will be 10 when T is smaller than 0. Next we have 10 exponential minus 1000 T when T is larger than 0 to 0.001. Then there will be 3.68 exponential minus 500 T minus 0.001 when T is larger than 0.001. Everything here. So if we draw this figure, the current, it looks like this. Here and here, there will be time, millisecond. So 1 and 2 and 3. We will start 10. This is IT. We will start here. At first, from this area is going down using that waveform here. So there will be 3.68 because current is not changed instantly, so will be reduced here this way. So there will be 10 minus 1000 T, and that is exponential minus T minus 0.001. So this is a complete solution in the case 2 switches in 1 second. So this is the way how to solve the sequential circuits. Next topic over here is stability of first order circuit. Now, what is of stability? Stability is a big problem when circuit design. I mean, for example, you can say the stability is quite quite complex problem. This is big problems. This is the huge topic to discuss here. For example, we have some system. We insert some input, and this is output. So if we insert the bounded input, then output is bounded. Then we call that is a general stable. System is stable. In Korean, 안정적. What's the meaning over here? If we insert some variable in some bound, for example, in max and in min, we adding some in general. This is time. This is time. We adding this kind of input here. Then output has this is time. This is output. The value is looks like complicated, but the values placed in the bounded values, bounded range here. Then you can say the system is stable. What is unstable? Even though input is inserted in some bounded area here, then output is not bounded in this way. This is going up, infinity. Then you can say the system is not stable, or we call this as unstable. So system should be stable when you design. So stability is back problems when you describe the electric circuit.